Professor Chii-Dong Chen.
Okay. So my talk will be much more engineering, and we are working very hard toward a 5-qubit quantum computer, and so my talk here will be about an optimization of the quantum gates that for a 1D chain of 5-qubit system. And so the first part will, of course, I say a little bit about our lab facilities and basic qubit characteristics and so on. And then I will tell you about optimizations of, say, a little bit on readout and then on control parameters and for single qubit gate, 2-qubit gate, and 5-qubit gates and so on. So basically, this is our QPU, which contains 5 qubits. They are just placed in a 1D array, and then they coupled to each other through just direct capacitive coupling. And these are we did some investigations on the packaging and so as to minimize any infrared or any any excitations from outside. And so this is how a photo of the system looks like. Well, we have 2 types of packagings here, and then so with this packaging we achieved a temperature not excellent, but finally from we was beginning well beyond 100 millikelvin, and finally we reduced to 40 millikelvin and by doing a lot of trimming on the packaging and those things. And so and with that the readout fidelities goes to 0.95 and so on. Yeah, and so this just shows a photo of our qubit chip fabrication facilities, and which is located in our institute. So we have electron beam writer and everything needed for the qubit fabrication. Of course, not to compare with the Lincoln fibers. Okay, yeah, and so and then. So this is our measurement system that, in the case of single qubit. So of course, so you might have known that it has an Y9 and Z9 and readout in, readout out. This seems to be very thin. Okay, and so 没有光线。Okay. Okay, but let's continue. Anyway, so this of course a very, very standard QPU design that with readout resonator and qubits and so on. So and we have readout we design in a way so that 所以我现在用这支吗？还是好这支吗？很恐怖呢，做这种事情啊，糟糕了。Okay. So far, so good. Yeah, and so okay. So this is our readout free-line coupling strength, and by design, and then so the resonator frequency we placed to 5.7 to somewhere 6.3 gigahertz. That is fit to the 2-part that we are using, and then the qubit resonator coupling strength we set it to 60 megahertz and corresponding to a time scale of 17 nanoseconds. And qubit frequency 30.5 gigahertz, and with a T1 time not very good, but okay, acceptable. And the best value we got so far is 32 microseconds only. So this is just a histogram of how it looks like. And so and I just put this slide in because I just find that Professor Oliver gave a talk on the excellent work that he did, but perhaps in the audience maybe there are some people that don't quite know what is going on there, how is the measurement made, and so this is just a simple graph to illustrate what's going on there. And so say that we have an FPGA and then like a control system that gives us eventually give us microwave signals, and that to want to make a readout, and the other one to control qubits, and then the signal goes to the resonators and cavities, and then goes out, and then finally is being read by the ADC, and then converted that into computers, and then give us the IQ signals. Okay, just in a few seconds finish this. And then so now, this is about the readout of the qubit state. Again, just simple illustrations. And so we consider that qubit as a two-level system, as Professor Oliver already explained. And then we have a resonator. Of course, this is, say here is a half wavelength resonator that coupled to the qubit, and therefore that makes the qubit frequency shoots. Of course, the resonator frequency also shoots, and then that this means there is an entanglement between the resonator photon and the qubits, and so on. And then so in reality, what we do is, and then we have a qubit with XY control, and then we have readout cavities, and this shows how it's in reality how that corresponds to those put on the chip, and then we have a readout line that finally gives us the IQ probes. And then these two probes, one is we prepare in a grounded state. That means we do no excitations, and then we see how where it is, and then we prepare in the excited state, and then we can see this. And so hopefully with 2 parts and those parametric amplifier, we can separate it even better. And so and then with this, we can continue to do 1 qubit and 2 qubit bring up and calibrations. And for this, and of course, we need lots of steps. Say just going from top down, study the spectroscopy of resonators, and pause the qubit spectroscopies, and then everything goes down, and finally we can read out know T1 time and T2 time, and then also for 1 qubit we do routine calibrations to optimize the qubit operations. So I will later tell you some items there say what we do in all XY steps, and what does that mean, and then so that we can make and randomize the benchmarking to see how the 1 qubit performance, and then we do 2 qubit calibrations and swap spectroscopy, as Professor Oliver mentioned, and then cryoscopes and all those steps, cryoscopes here, yeah. And so say, and we can to start with, we need to find out the driving frequency and powers, and for the to drive a single qubit. And so this, we can do a driving frequency span, and then with different driving power. So we call this power Rabi. And so with this, we get Rabi chevron, and then we can also retrieve across frequency and power for the pi process. And then once we know pi path